continuous systems, transverse beams. At the end of this section, you should be able to identify homogeneous boundary conditions for beams in transverse loading. And you should be able to solve the partial differential equations with homogeneous boundary conditions for the natural frequencies and the eigenfunction for transverse vibration. In this section, we're looking at beams that are undergoing transverse oscillations. This is in contrast to what we did before, looking at axial bars that were going to move along their longitude. Here, our beams are going to be moving in, at least as pictured here, the vertical direction. And we're going to be looking at beams that are experiencing no axial force, only internal bending moments and shear force. So what we're going to be trying to find here eventually is what is the vertical position of our beam at every point x and at every point in time t. So we can start with our very general beam in bending over here, and potentially we could have some distributed loading that can change in space in the x direction and also change with respect to time. And we're going to see that the vertical position w of the beam is going to be different as we go along x, and because it's a dynamic system, this w will also change in time. So eventually what we're interested in is solving for this w of xt. Like what we did with axial beams, we can derive the governing equation, the equation of motion for w, by taking an infinitesimal slice in our beam in bending, and we'll blow it up over here in picture B. And what we see here in our model, since it's infinitely thin, we're going to have some internal bending moment m. We'll have some internal shear force V on the left side at this point O. And then we go infinitesimally to the right at this point O prime, and we're going to see we have a slightly different internal shear force V plus a dV, and a slightly different internal bending moment in M plus a dm. So a dm can be positive or negative, but it's going to be very small. Same idea with dV, it's positive or negative, but very small. And because dx is very small, we're expecting that the change from left to right of the internal bending moment and the change in the internal shear force, therefore, to be very small. So we can use this cutout piece, this infinitely thin piece here, to derive some equations using Newton's second law. So if we start by summing the vertical forces in picture B, we can sum them up, and we're going to get the mass times the acceleration of this piece. So on the forces side, pointing down in the picture is the V plus dV on the right. We will have this distributed loading F acting across a distance of dx. So the intensity of F times the distance dx gives us the force. And then on the left side, pointing up, we have our internal shear force on the left, V. And then on the right-hand side here, we have our mass times our acceleration. So the mass is going to be the volumetric density times the volume of this piece. So each of these pieces here is going to have a cross-sectional area that could change as we go left to right in principle, and potentially the density could change as well in space or in time, and we'll address that as we go further in this derivation. But the cross-sectional area times the length is going to give us the volume of our infinitesimal piece. The volume times the volumetric density will then give us the mass of our infinitesimal piece, and then we can look at its acceleration. Since we're saying it's only moving in the w direction, it's not going to be moving left-right, there is no axial force, and as we're going to see in the derivation using the moments, it's also not going to be rotating. It's purely translating in this z direction, this w direction. So therefore its acceleration in the vertical direction is going to be the second derivative of its vertical position. So partial square w partial t squared is going to give us its vertical acceleration. And we want to keep in mind that w is a function of both space and time, so this is just the second time derivative. So we can take that sum of forces and we'll put it aside for the moment, because we can also take the sum of moments around a point on our picture. So if we take the sum of moments around point O, we can see what are all of the moment effects. So the internal bending moment in the positive counterclockwise direction, we have the m plus the dm. In the negative clockwise direction, we'll have m, so minus m at the end here. We are through O, we have v, so it does not appear in this equation. However, we do have this v plus dv that is a distance dx away. So that appears as our second term here. That's the moment it causes around point O. And then the moment that this distributed load is going to cause is going to be the density times the length is the force, so F times the dx. And for this very small piece, we can assume that the intensity is uniform, which means that we can put its equivalent loading location at the center, so dx over 2. And we are going to presume that in these transverse beams in bending, that these segments do not rotate. They experience only a vertical displacement, but not a rotational piece. Therefore, the right-hand side we can say is 0. There's not going to be rotation considered for these beams. So we have a sum of forces equation, we have a sum of moments equation. Where we're going to try to get to is an equation of motion that is going to tell us about W, that we are then going to be able to solve in another step. But first, we need an equation that tells us how W is acting in terms of space and time. We're going to need to get to a partial differential equation. So let's start with our first equation, the sum of vertical forces, and start to make some simplifications here. So looking at the equation we made, we are going to have here this positive v and this negative v, and those are going to cancel each other out. So that's the first modification we can make, or simplification we can make. And we have this dv term. As we saw with the axial problems, we are going to be able to write dv as a del v del x dx. So with these two small simplifications, we can now rewrite this a little bit more simply here. And we can simplify it then a little bit further. Because at this point now, everything has a dx with it, so the dx's are all going to be able to cancel out. And finally, we can rewrite the sum of vertical forces. Here we have a del v del x term. We have our loading intensity as it changes across left to right and in time, and then our density, our area, and then the acceleration, the vertical acceleration. So once again, I will take this more simplified version of the sum of forces and put it aside for the moment. And let's go to the sum of moments equation and make some further simplifications there, and we'll see how we're going to bring them then together. Looking at that sum of moments around point O equation that we had before, again, we're going to have some things that drop out. We have an m, I have a negative m. Those are going to be able to cancel each other out. This dm, like we saw before, I can rewrite as partial m partial x dx. And again, the dv can be a partial v partial x dx. So we can rewrite this then thus. At this point, I have a bunch of dx terms. I can get rid of a dx here, and a dx here as I go through. So I still have some things that still have dx terms, but I can make one more simplification here. I'm going to say that because dx is going to be very small, I can actually get rid of the terms that still have a dx attached to them. So this term, because it's being multiplied by a dx, is going to be relatively very small compared to terms that are not being multiplied by dx. And the same idea here, this term is going to be able to be relatively negligible compared to that del m del x and the negative v term. So with further simplification, the sum of moments around point O is going to reduce to this del m del x minus v is equal to 0. Now I have a simplified version of my moment equation, I have a simplified version of my sum of forces, and now I can bring them all together. So on the left, I have my sum of forces equation simplified, and on the right, pulling that v to the right-hand side, I now know that del m del x is equal to v. And actually, I already knew del m del x was equal to v. We know this all the way back to strength of materials. If we think about a VM diagram, one way we can draw the M diagram is by integrating v. As this is saying that the Spatial derivative of m is v, therefore the integral of v gives us m. And when we're drawing by hand the VM diagrams, that is exactly what we do. So I can start to combine this because I have a v term on the left equation. So I'm going to be able to substitute in here. Instead of having a v term, I'm going to be able to have an m term. So combining these two, I now get this second spatial derivative of m on the left-hand side, plus that loading intensity equals that rho a times the acceleration. Now in strength of materials, we didn't see this. We didn't have a relationship between the acceleration and what the bending moment was, because in strength of materials, everything was in static equilibrium. But now we have a dynamic problem happening. But we do know from strength of materials that we have this constitutive relationship. And what that means is it's the relationship between the material properties and the bending or the curvature of the beam. So we know all the way back from, again, strength of materials, that that bending moment is EI times the curvature, which we can also write as this del squared W del x squared. And potentially this E and this I can both be functions of x. If the material changes left to right, E could be changing, and if the cross-sectional area changes left to right, then I can be changing. So this is another definition of M from the material standpoint. So I can take this combined equation along with the constitutive relationship, and now this is another combination where I can put in, for M, this expression, and do another substitution and actually get the bending moment out by substituting it out. So combining those, I'm actually going to get then the second spatial derivative of now this stuff, the EI del squared W del x squared, and then I still have left over the rest of this. And you'll notice here that I did some rearranging here so that I have, instead of a negative on this material, I put it on the other side. So I now have positive, my first term plus the rho A is now on the left-hand side equals F. So now everything is positive the way I have it written. At this point, I'm going to make some limitations or simplifications. We're only going to be considering analytically beams that have constant material and constant shape. So what that means is that if my material is constant, this E can come outside of this derivative. For constant shape, this I can come outside. They are not going to be functions of x now with this limitation. The same idea with my A is going to be constant, and I didn't have it written here, but rho is also going to be constant. So that means since E and I can come out of that first term, I now am taking the second derivative of the second derivative of W, and I'm going to be left with then the fourth derivative of W, which again, W is the position, this is the fourth spatial derivative of the position, plus this rho A del squared W del t squared. So now I'm at the point where my equation has a fourth spatial derivative, it has a second time derivative of the variable I'm ultimately looking for, W. So one more simplification we're going to make that is going to make this a more solvable system analytically is we're also going to limit our scope to free vibrations, meaning that we are not going to have a loading, we're not going to have a distributed load after time begins. It's going to be 0 once the timer starts. So finally, because the right-hand side is 0, I can divide everything through by this rho A, and now I get this partial differential equation here. I have here c squared times del to the fourth w del x to the fourth plus del squared w del t squared equals 0. And I have this c term. It looks kind of similar to what we saw for the axial problems or the string problems. This c is going to be determined by, well, geometric properties I and A, and material properties E and rho. And we're going to now have this partial differential equation, but now instead of it being second order in space, we see it's fourth order in space. And it's still going to be second order in time. So the form looks a little bit different than what we had before. The solution, because it's fourth order in space, is also going to be a little bit more difficult, but we're going to investigate how we can solve for W in a general sense, and also how do we find the natural frequencies, the eigenfunctions or mode shapes of transverse beams. But again, to quickly recap, this PDE is coming from a beam where the cross-section is constant. It's a single uniform material, so E and rho are going to be constant. And it is a free vibration, so there is no distributed load happening. It's only going to be oscillating based on the initial conditions of the beam.